Okay, so I guess I'll get started. Allow me to introduce you to what I hope to be the first of many annual undergraduate computer science research lightning talks. I'm going to get started by talking about distributed computing. And the goal, as with most of my presentations, is just to get you to understand the title. And if I can do that, then I've succeeded. So let's get started. Distributed system is just a collection of computing devices, which we call processes, which can communicate with one another. So examples are modern laptops, which have multiple processors, LAN parties, network computers, the internet, which is a slightly larger network, and people, technically, I think it satisfies the definition too. So distributed computing focuses on how those processes coordinate actions. And it's different from parallelism, which you may have heard of, which parallelism focuses on taking a big job and breaking it down into smaller jobs, which the processes can solve. And the systems tend to be very tightly coupled and not very failure prone, whereas distributed computing is very loosely coupled systems. All sorts of failures can happen, and the processes tend to operate independently of one another. And the only reason they need to communicate at all is because they might be competing for resources like memory or a printer, or to achieve fault tolerance, like a database. So that's actually a pretty big definition, so we need to talk about specific assumptions like synchrony, fault model, and communication methods. So when I'm going to say that I'm going to be talking about asynchronous methods of communication, I mean that the times at which these events take place can't be known precisely. So in particular, you don't really know how long or short time you have to wait for the next event to take place. So when you're proving a distributed algorithm is correct, you need to consider all the different ways that these executions of programs can get interleaved. So here, process B finishes its entire process, process B finishes its entire operation, and then process A does it, right? So you need to consider all of those for correctness. And for our fault model, processes can crash at any time. And when I say crash, I mean that they'll just stop executing without any kind of warning. So this is a particular problem for asynchronous models because, loosely speaking, in general, you can't tell whether a process has crashed or is just taking a very long time to finish its operation. Another kind of fault model that I won't be talking too much about is Byzantine faults, where some processes just stop following instructions and do their own thing. This might be due to malicious action, like a hacker trying to take over the system, or it might be due to incompetence. My favorite example of the latter is when a single corrupted bit in an AWS network packet caused the entire infrastructure to become unresponsive for 8 hours. So that was a system that wasn't resilient to Byzantine faults. And for a communication method, processes will be communicating by just reading and writing to shared memory locations. Another popular way is using message passing, or even a hybrid of the two, but we're just going to be focusing on the first. So to summarize, asynchronous processes, we don't know when events are going to happen. Processes can crash at any time, and we're communicating with shared memory. So let's go over a simple example where two processes are trying to increment a shared integer called x 4 times each. So this is their program. They just increment it 4 times, right? And so if our program is correct, the result after they're both finished is that x is equal to 8. I hope you can see that. So here's an example of an execution where process A increments, process B increments, and because it's asynchronous, all these different events might be rearranged, or save questions for afterwards, sorry. So where was I? I didn't prepare for interruptions. Okay, so this should be okay it appears to be okay in an asynchronous model because increments can be rearranged, right? It doesn't matter as long as you increment the same amount of times. But actually, this instruction is a lie propagated by Java and C compilers, because this isn't a real thing that your computer can do. X memory locations are actually registers, which only support read and write operations. So this instruction actually gets turned into this, where X is read into a temporary process local variable, and then that new value is written back to X. So it's actually 2 steps. And the significance is that this code actually is this, and that means that our execution actually looks more like this, which is a problem because now these 2 steps can get rearranged. So Now, process B reads 2, and process A reads 2, and they're both trying to increment, but only one of that increment actually happens. Hence, 1 plus 1 equals 1. Ha ha. So it's incorrect for asynchronous models. Now, you might be thinking that we can use locks, which, if you don't know about them, are a way of establishing mutual exclusion. So a process says, I'm going to perform these instructions, and nobody else can perform these instructions until I'm done. Well, so if we rewrote our code with locks, it would look like this, which means our execution would look more like, spoiler, looks more like this. So process A locks, does some things. Process B starts, but it has to wait, right? And then, OK, process B gets the lock, but because we have to be fault tolerant, if it crashes, this is a big problem, because then process A is stuck waiting forever. So this algorithm isn't fault tolerant for asynchronous models. So locks are not an option. Probably shouldn't drink water now. Luckily for us, most CPUs have a handful of what are called atomic instructions, which are more expensive, but they perform what normally would be several instructions, apparently instantaneously. So an atomic instruction appears to take place instantaneously to all the other processes. So an example might be fetch an increment, which just increments the variable x and also returns its old value. Well, this is perfect because that satisfies our use case exactly. If we replace these two instructions with an atomic instruction, then we get the reasoning that we had before. We can rearrange all these different fetch and increments. Doesn't matter. So this is a correct asynchronous fault-tolerant algorithm for a completely useless problem. So I should have like a minute or so to talk about actually my work from 2 summers ago with Professor Faith Ellen. I was talking about what I was working on was manual memory reclamation for dynamic data structures, which are like linked lists and trees where you can add and remove nodes in a distributed setting. So for example, if you have this distributed tree, all these nodes are in shared memory, and processes are crawling all over it, traversing it. And suppose that this pointer gets removed. So this part of the data structure is removed, right? Well, even though it's not reachable, we can't say that there are no processes accessing this. So if we decide to just clear off the memory to free the memory that B and C are using, then B and C would try and access the memory not knowing it, and it would be an invalid memory access, which at best is a crash, and at worst is a corrupted crazy data structure. We don't want that. So this part is unreachable, but is occupied. Reachability is easy to find out solutions for, but occupied is a little bit different. So let's quickly talk about that. One solution, or attempt at a solution, is to give each node a count of the number of processes. So when you say, I'm about to access this node, so I'm going to increment the node's process count, and then when I'm done, I'm going to decrement it. The problem, of course, is that you're kind of begging the question. I'm going to access this node in order to access this node. So more concretely, what would happen is B is trying to access this node. It wants to increment the process count, but the node gets deleted. Process A decrements the process count. It says, oh, nobody's using it. Removes the memory. B is sad. So instead, we're going to use a trick from Hyun-Ho Lee's PhD thesis, which was in a very particular different data structure. We're extending it, where we're going to give each pointer this proactive count, right? And in order to use a node, you atomically read the pointer to that node and increment the count. And when you're finished with it, you decrement DRC, a distributed count associated with each node. So for example, here, B tries to access this node. So it atomically reads the pointer and increments this PRC. A deletes the pointer, but because the PRC is 1, it decides to pass on this number of processes down to the DRC. So now DRC is 2. A is like, goes somewhere else, but it doesn't delete the node because this DRC not equal to 0 means that somebody's about to access it. And so B gets there and B is happy. So the problem was that the node is deleted before the process count was incremented, and a trick is to atomically read the pointer and increment the proactive count at the same time. The problem, though, is that most distributed data structures already use atomic primitives for managing those pointers, and they're kind of incompatible with this method. So the solution to that is so cool, but unfortunately I'm all out of time. So thanks for listening. This is a QR code for my website with a transcript and some works cited. Thank you. Turn it over to you. Go ahead.